Look around the parks and bus stops of southern Israel, and you'll quickly notice these concrete boxes. They're an everyday piece of the landscape, built to give anyone nearby immediate cover during a sudden rocket alert. They're called migunits. From the outside, they look incredibly secure. The reinforced walls are poured thick, projecting absolute, unshakable strength against falling shrapnel. When you only have 10 or 15 seconds to find cover, seeing a massive block of reinforced concrete gives you an immediate sense of relief. You step inside and your brain tells you that you are protected. This heavy exterior establishes a strong feeling of safety, but that feeling is based entirely on the visual thickness of the walls. To see if that protection actually holds, we have to look past the concrete and into the geometry of the entrance. Because despite all that reinforced concrete, the classic migunit has a distinct structural anomaly right at the entrance. There is no actual door. In the official architectural blueprint, the main entrance gap measures between 80 and 110 centimeters across, completely exposed. To compensate, an L-shaped partition wall acts as a baffle, designed to catch shrapnel flying through the doorway before it reaches people inside. This layout hinges on one very specific assumption about warfare, that the only threats will be rocket artillery detonating yards away in the street. A blast wave expanding outward from a distance doesn't easily hook around sharp 90-degree corners. The geometry makes sense for a distant rocket strike, but combat is rarely that cooperative. When the threats on the ground adapt, a static concrete blueprint quickly becomes a liability. The design changes its behavior the moment an attacker walks right up to the entrance. When you introduce close-quarters weapons like targeted grenades, RPGs, or small tactical drones, the rules of blast deflection change entirely. This diagram illustrates what happens when explosives are fired directly into the 80-centimeter opening. The high-velocity blast hits the rigid interior partition and ricochets. The flat walls bounce the blast wave straight past the baffle, funneling directly onto civilians huddled in the back. The structure built to absorb an attack acts like a funnel. It catches the expanding pressure and channels it violently into the tightest, most densely packed area of the room. A drone flying into the doorway, or gunfire swept into the opening, leverages this exact deadly geometry. The bullets and the blast wave bounce along the concrete path with brutal efficiency. It creates a grim paradox. The outer shell of the migunite is thick enough to survive almost anything, but once an attacker crosses that open threshold, the people inside have literally nowhere to hide. By leaving the entrance open, the architecture takes what could have been a survivable external blast and amplifies it into an inescapable trap on the inside. The frustrating part about all of this is that the physics of protecting a doorway aren't a mystery. Engineers solved this precise problem generations ago. This 1942 sketch of a German civil defense shelter relies on completely different geometry. Rather than flat internal baffles, the exterior itself is circular. The rounded shape forces incoming shockwaves to glance off and dissipate outward, rather than boxing the pressure inside. But more importantly, these World War II designs mandated heavy, reinforced steel blast doors on strong hinges to completely seal the entryway. While open entrances are easier to maintain and faster to enter, they represent a significant departure from these decades-old standards of a fully sealed, blast-protected entryway. It took catastrophic, real-world failures to finally break the reliance on that L-shaped design. After taking devastating casualties, its standards for public shelters are undergoing a rapid overhaul. Across vulnerable communities, you can now see heavy cranes dropping a modernized generation of shelters into place, built to address the flaws of the past. The internal baffle system is gone. The most significant structural change is the abandonment of the open-air gap in favor of a completely sealable entrance. These new models feature thick, heavy metal doors built directly into the concrete frame, complete with internal locking mechanisms. It's a simple fix, but it definitively ends the funnel effect. A locked steel barrier physically blocks drones, grenades, and ricocheting bullets at the threshold, forcing the kinetic energy to dissipate harmlessly outside. This does introduce an operational trade-off. A heavy blast door requires a conscious physical effort to pull shut, which costs precious seconds during a frantic scramble for cover. But once closed, it provides absolute separation from the threat. True engineering resilience involves acknowledging when a blueprint fails to match the reality of a threat, and returning to basic physical principles to fix it.